Yeah, hello everyone. Uh, this is RC Circuits lecture number 2. So, in lecture number 1, we have discussed the basics of resistor, capacitor, and inductor, and a simple series RC circuits, and we have derived all the voltages and all the currents. Yeah, this effective current through the circuit, and we have concluded the definitions of time constants. It is different for two cases. One is the time taken for the circuit to reach 63.2% of its final value, and another one is the time taken for the circuit to reach 36.6% of its initial value. And we have seen that for a series RC circuit, the time constant is multiplication of R and C, and we haven't seen for RL circuit, and we will see that today. So yeah, we will cover this basics of capacitor and inductor just to refresh again. So how the capacitor acts in transient circuits. So whenever some switch is closed or switch is open for DC inputs, this is only for DC inputs, then we replace the capacitor with its initial voltage. Here initial voltage is V0 and capacitance is C. So at t is equal to 0 plus, I am assuming there is some transient in the circuit at t is equal to 0. So at t is equal to 0 plus, we represent the capacitor with its initial voltage V0, and for t greater than 0, we represent the capacitor with initial voltage of V0 and then the capacitance. For t tends to infinity means at steady state, we represent the capacitor with open circuit, assuming it is charged completely and there is no current flowing through that capacitor further at steady state. And we have already discussed what is meant by steady state and how much time it will take to reach the circuit to steady state, that we have discussed in the previous lecture. And similarly for inductor at transients, this is also only for DC inputs. We will discuss later for what will happen to the capacitor for AC inputs. We will actually keep the capacitor same, that if we solve some problems, then we will feel some better. So for inductor also, for DC inputs at t is equal to 0 plus, again I am assuming there is some transient in the circuit at t is equal to 0. So at t is equal to 0 plus, we have to replace the inductor with its initial current, which is I0, and for t greater than 0, we will represent the inductor with its initial current I0 in parallel with that inductor. And for steady state, for t tends to infinity, we replace the inductor with short circuit. So this is how the transients circuits will work for t is equal to 0 plus and steady state, yeah, for both inductor and capacitor. Now we will quickly go through what is meant by order of the circuit. So what is meant by order of the circuit? Order of circuit is defined by the number of effective storage elements in the circuit. So number of effective storage elements in the circuit. If you remember from your engineering mathematics, from differential equations, what is meant by order of a differential equation? It is the highest degree of that equation. Suppose if you have some d square y by dt square and some constant times dy by dt, some constant, then is equal to 0, then This is a second order differential equation. Similarly, for a circuit, if you derive some expression from the circuit, if you write the current flowing through any element in the circuit, then you will get the second order equation if the circuit is second order. It means if the circuit has two effective storage elements, then you will get second order differential equation. Then we call the circuit as second order circuit. This effective is important. It means, suppose for example we have this circuit. Here we have two capacitors C1 and C2. It does not mean the order of the circuit is 2. This is wrong, because we can combine these two capacitors, right? So we will write this circuit with only one capacitor by combining these two. So this is effectively first order circuit. So that is what the effective meaning. And also similarly, if you have a capacitor and a capacitor here, and if you want to find the voltage here, then if you derive the expression for V0 of t, if you have some input voltage, we can take step input, and if you find V0 of t, then you will get first order equation. So it means we can combine these two capacitors, right? So these two capacitors are in series, so we can combine these two, and you will get the first order equation. So this circuit is first order circuit. So the order does not mean the number of storage elements, it means the number of effective energy storage elements. And also we can say the order is number of independent variables, number of independent variables. For the storage elements, we have only inductor and capacitor, right? So here we can take the independent variables, the variables as Vc of t and IL of t. So these two are two different variables. So it means let's take the simple, these two are in parallel, right? These two capacitors are in parallel. So if you know any one of the voltage across any one of the capacitor, then you will know the voltage across another capacitor also. So if you know Vc1, then indirectly you know Vc2 also, right? So it means Vc2 is depends on Vc1. So it means the number of independent variables are only one. If you take any one as independent variable, then another variable is depending upon the opposite voltage. So we can say like this also. So it is the number of effective storage elements, and it is the number of independent capacitor voltages or independent inductor currents. That is how we can define the order of a circuit. So we can just write some examples. So this is first order. Vc1 is equal to Vc2. So these two are dependent, and a series RLC circuit. Is this a first order or second order? Definitely this is a second order circuit, because this is I of t and this is V of t. So if you write KVL, you will get a second order differential equation. So this circuit is second order. And I think we can write KVL here. So V in minus I of t into R minus L times di by dt minus V of t is 1 by C integral I dt is 0. If you differentiate this equation, then you will get d V in by dt minus R times di by dt minus L t square I by dt square minus 1 by C I of t is equal to 0. So if you want to solve this equation, you have to solve using second order differential equation method. If you want to find I of t, then you have to solve this second order equation. So this circuit is a second order circuit. And we have discussed about the time constant. So we have seen the time constant for a series RC circuit is R times C, and we generalize this time constant for any first order circuit. This is only for first order circuit. So for first order circuit, for any first order circuit, if it has some capacitors and resistors, then time constant is R equivalent times C equivalent, and for RL circuit it is L by R. So using these two, we can find the time constant of the circuit of first order circuit. Then we can solve the voltage or current, anything in that first order circuit. So how to find C equivalent? C equivalent is, if it has only one capacitor in the circuit, then C equivalent is nothing but C. Or if it has multiple capacitors and they are effectively can combine, then we can combine those capacitors similarly like this, and we can write that C equivalent. And what is R equivalent? R equivalent is the effective resistance seen from capacitor terminals. What is meant by effective resistance seen from capacitor terminals? It means we have to replace all the independent sources with 0. It means the voltage sources should be short circuited and current sources should be open circuit. Then across the two terminals, if you find the resistance, then it is R equivalent. Then if you multiply that R equivalent with C equivalent, then you will get the time constant. So in a series RC circuit, we have got directly R into C, because if you see from these two terminals of the capacitor, if you replace this input voltage with the short circuit, then you left with only R. So R equivalent is simply R here, and there is only one C. So R into C is your time constant for this circuit. And similarly, you can find L equivalent and R equivalent also. Here R equivalent is effective resistance seen from the inductor terminals. So this is done, and we will write the generalized expression for a first order circuit. So if you remember, for a series RC circuit, we have got some output voltage across the capacitor as some V in times 1 minus e power minus 1 by RC into t, 1 by RC into t into u of t, something like this. So this may vary from circuit to circuit. This we cannot remember, right? So we can go for a generalized expression. So what does it mean? So for this is also only for first order. So for any first order circuit, the voltage across the capacitor is final value plus initial value minus final value into e to the power minus 1 by R equivalent times C equivalent into T, which is final value plus initial value minus final value times e to the power minus T by tau. Similarly, the current flowing through the inductor in a first order circuit is final value plus initial value minus final value into e to the power minus R equivalent by L equivalent into T, because tau is L by R. So you will get e power minus R by L into T. So if you remember this one, then it will be very easy to solve any first order circuit. So IV is initial value. How will you get the initial value? It has to be mentioned in the problem, or yeah, this if we solve some problems, then it might be some in between from minus infinity to infinity, in between, like if there is any transient, so before the transient we will take that value as initial value. So while solving the problems we will discuss that one. And final value is, you replace the capacitor with open circuit, then you will get the final value, and if you replace the inductor with short circuit, you will get the final value of that RL circuit. And this is good enough. And if you remember this expression, and if you understand the difference between first order and second order, and if you know about this steady state and t is equal to 0 plus in transient circuits, then we can easily solve first order circuit. So today we can solve these circuits. We can start with this circuit. Yeah, So here in this circuit there are two resistors and one capacitor, so directly it is a first order circuit. And there is some transient it so the switch is closed at t is equal to 0. It means we are applying a DC voltage at t is equal to 0. Till t is equal to 0 it is 0. And so we are applying 15 volt to the circuit at t is equal to 0. So this is step input, right, with amplitude of 15. So V in of t is, in math we can write 15 u of t. And what is the time constant of the circuit? So time constant is R into C, R equivalent into C equivalent. So C equivalent is 0.4 times. What is R equivalent? So you have to short circuit this voltage source. Then if you see from these two capacitor terminals, then it is nothing but R equivalent. So here this resistor is connected between these two terminals, and this resistor also is connected between these two terminals. It means these two resistors are in parallel. So this is 8 ohm and this is 4 ohm. So since these two are in parallel, we can directly write 4 into 8 by 4 plus 8, which is 12. So you will get R equivalent as 8 by 3. So this is 3.2 by 3, which is approximately 1 point something. Let's see. So this is 1.066 seconds. It means if you wait for 1.06 seconds, then the capacitor voltage will charge to 63% of its final value. So initially it has 0 initial voltage. Since it is not mentioned, we can take it as 0, and it will go to some steady state. We don't know. We have to find the steady state. So at steady state, t tends to infinity. So at steady state, the capacitor is fully charged and there is no further current flow. It means it is open circuit. So if it is open circuit and there is no current flow here, so this is 15 volt. What is this voltage? So Vc of infinity is, it's a voltage divider. So it's 4 by 12, which is 5 volt. 3, yeah, it's 5 volt. So it will not charge to 15 volt. It will charge to only 5 volt at steady state, right? It's not even 5 volt. Yeah. So yeah. this is Vc of t. So this will charge to 5 volt. So some 63% of it is 1.06 seconds. So how much time it will take to reach the voltage to 5 volt? It will take, we have discussed, right, it is 5 times RC. So it is 5 times 1.06. It's approximately it's 5.33. So it will take this much time to reach this voltage to more than 99% of its final value. So if you wait for this time, maybe it has reached to 4.999 something. Yeah. So we can approximately take it as 5. And yeah, if you want to write the expression of output voltage, so you can check here. Suppose if is it reached to steady state or not at 5 volt, how can we know? So if it reaches to 5 volt, so this is 5 volt, right? So assume it is reached to 5 volt at some point, and here it is 15 volt. So this is 8 ohms. How much current is flowing through this branch? It is 10 by 8 amps, and this is 4 ohms. And how much current is flowing through this 4 ohm? It is 5 by 4. 5 by 4 is nothing but it's 10 by 8. It means whatever the current is sourcing from this voltage, which is 10 by 8 amps, is completely flowing through this 4 ohm, right? So it means there is no current flow through this capacitor. It means the circuit is reached to steady state. That is how you can cross verify. Right. Yeah, let it be. And what is the expression of the voltage across the capacitor? This is Vc of t. So Vc of t is final value, which is 5, plus initial value minus final value times e to the power minus 1 by RC. 1 by time constant is 1.066 times t. So Vc of t is 5 times 1 minus e to the power minus 1 by 0, sorry, 1.066 times t. So this is only for t greater than 0. So we'll write u of t. So before for t less than 0, it is 0. So we will write like this. And what is the capacitor current? And we can find any voltage right here. So let's say it is some V2, and let's say it is V1, and this is V2. So V2 of t is same as that of Vc of t, because these two are in parallel. And what about V1 of t? V1 of t is this input voltage minus this Vc of t, right? So V1 of t is input voltage 15 minus Vc of t, which is 15 minus 5 plus 5 times e power minus t by tau, which is 10 plus 5 times e to the power minus t by tau. So we can also derive this V1 of t using that generalized expression, right? So if you write final value plus initial minus final and everything, sorry, any V1 of t or V2 of t, so we can quickly write that. What is the final value of V1 of t? Since it is open, it is uh, these two are in series. So if you write voltage division here, here already we got 5 volt across this 4 ohms, right? So the remaining 10 volt you will get here. So the final value is 10. That is what you have got here. This is final value. And initial minus final. What is the initial value? Initially this is short circuited for t is equal to 0 plus. It means there is no 4 ohm here. It means the complete 15 volt will come across this 8 ohm. You understand it? Initial circuit is like this. It is short circuit, and we have complete 15 volt across this 8 ohm. So you will get initial minus final. If final is 10, initial is 15. So 15 minus 10, which is 5. So you will get the same. So this is initial value minus final value. So you will get the same expression. And what else we can find? We can find the current flowing through the this capacitor, right? So how can we find that current? So the capacitor current is C times dV by dt, which is 0.4 times dV by dt is 5 by 1.066 times e power minus t by tau. We can solve this later, but this is how it looks like. Some constant voltage, some k, times e power minus t by tau. So for t tends to infinity, it is going to 0. It means there is no current flow through that capacitor. And for t is equal to 0, it is this k. K is 0.4 times 5 by 1.066. Let's see how much we'll get that. Zero 0.4 times 0.066. So this is 1.876 times e power minus t by tau u of t. So for t is equal to 0, we have only this circuit, right? It is short circuited. So this is 15 volt and this is 8 ohms. So it's just I of 0 is 15 by 8. So 15 by 8 is 1.875. So yeah, it is approximately same. So you will get 1.875 times e power minus t by tau. It means at starting, since it is not charged when t is equal to 0 plus, there is some huge current flow. It is short circuit. It is 0, right? So it is short circuited, and there is more current flow through that circuit, which is 1.875 amps. So we can say this much. And whenever the circuit starts charging up, the capacitor starts charging up, the voltage will increase, and it is same as that of this voltage. So if this voltage is increasing, it means the potential difference, this is constant. So this potential difference is decreasing. It means this current is decreasing. And since this voltage is increasing, this current is increasing. This current is decreasing and this current is increasing. It means like you have, so I'm assuming this is my resistor 4 ohm side, this one, and this is my 8 ohm side. Let's say this is I1, and this is I2, and this is I3. So I1 is equal to I2 plus I3, and it means I3 is equal to I1 minus I2. I am saying I2 is increasing. It means the subtraction is increasing, so the overall value is decreasing, and I1 is also decreasing because the potential here is increasing. Effectively, the current is decreasing very fast. This I3, you understand? So this is decreasing and this is increasing. It means I3 is decreasing very fastly because of these two currents. So it will go to finally when I1 becomes I2, when I1 is equal to I2, then the current I3 will be 0. So that is how this will reach to steady state. So that is about this IC of t. And what about let's say this is I1 of t. And is the IC of t same as that of I2 of t? Definitely not. But Vc of t and V2 of t are same, but this IC of t is C dV by dt, but I2 of t is, it's just a resistor, right? So it's V2 of t by this 4 ohm, and I2 of t is Vc of t by 4, and similarly I1 of t is V1 of t by 8. Yeah, that is how you can find all the voltages and currents for this circuit. And now I think that is for this circuit. Anything can find, and we can solve one more circuit. So we will take this one. So at t is equal to 0, the switch is going from, maybe it is in position A and it is going to position B. So assuming for t less than 0, the switch is at position A for long time. So I am writing here, switch at position A for long time at t less than 0. So at t is equal to 0, it moved to position B. Let's analyze the circuit first at t less than 0. Long time means the circuit has reached to steady state, right? So this is 100 volt and 10 kilo ohm. So this is a RC circuit that we have already derived, right? So for t less than 0, or we can draw here, so Vc of t for t less than 0, let's say we have applied this 100 volt maybe at some point, so maybe here. So here it was 0 initially, the capacitor voltage was 0, and we have applied 100 volt here. So this will finally, it will be open circuit, so this will charge to completely 100 volt, and there is no resistor divider here and nothing. So it will charge to completely 100 volt. So and that will be in exponential, so from this to 100 volt in. So here I am writing time constant, and this is phi tau. So the time constant is RC. We don't know this time, so better if you write this is time constant and this is phi tau, and what is tau? It is RC. So 10k times 0.5 microfarad, so which is 5 millisecond. And for phi tau, which means after 25 milliseconds of this voltage is applied, then the circuit will reach to its steady state. It will charge to 100 volt completely and it will stay here for a long time. So this is phi tau and this will be 100 volt. So what will happen here? At t is equal to 0, there is transient behavior in the circuit. There is some change, some switching action. So this is for t less than 0, and for t greater than 0, there is a capacitor and resistor, and these two are in parallel. And 240 kilo ohm. Yeah, this is how the circuit looks like at t greater than 0. Now it has some initial voltage. That is what I meant. Here initial voltage is not 0. We should not take it as 0. It is already charged to 100 volt and there is some transient behavior after this t greater than 0. So at t is equal to 0, we have some voltage across the capacitor that we take as initial voltage for the analysis of t greater than 0. So here the initial voltage is 100 volt, and yeah, this is a first order RC circuit without any independent source in the circuit. It means there is no DC voltage source or DC current source in the circuit. So the capacitor will not charge further. It will discharge through the resistor. So if you analyze this circuit, it will discharge completely to 0. We will calculate the time constant later, but this is how it looks like. This will completely discharge to 0. So now we can call this as time constant. See, the time constants are different for both the circuits, right? So here the time, let's say it is tau 1 and this is tau 2. So what is tau 2? C is 0.5 micro times R equivalent. R equivalent is these two resistors are in parallel. So you are looking from here, right? And there is no voltage source and current sources to kill short circuit and open circuit. You can directly take the equivalent resistance from looking from here. So if you look from here, these two are in parallel and the effective resistance is in series with that 32k. So 60 R equivalent is 60 times 240 by 300 plus 32. So how much will get? 240 by 5 is 48 plus 32 is 80. So R equivalent is 80 kilo ohm. What is tau 2? It's 80 kilo times 0.5 microseconds. So 80 times 0.5 is 40 and this is 40 milliseconds. So, and here tau 2 is 40 milliseconds. It means, what does it mean? The capacitor is discharged to some I don't remember exactly, 36% I think, yeah, 36.6% of its initial voltage. It means at this point the capacitor voltage is 36.6 volt. So it is discharged to this much value at tau 2. So and it will go to more than 90%, 99% of its initial voltage. I mean, it is decreasing. It means it is very near to zero. It is even less than 1% to that zero, which is 5 tau 2, right? And tau 2 is 40 millisecond. Now we can write the expression for Vc of t now. So Vc of t is, so this expression is, so this one is uh, for for this circuit, what is the final value? You ignore the final value. For the complete circuit, the final value is 0, that is sure. But for only this circuit, I mean, this circuit doesn't know, right? The circuit doesn't know that there is some transient behavior is coming at t is equal to 0, so I have to take the final value as 0. So it doesn't know. So you assume in place of circuit. So it is assuming that I am going to reach the final value as 100 volt. That is what it knows. So final value is 100 volt for this circuit and initial value is 0. So you will get 100 times 1 minus e power minus t by tau 1, right? That is what this expression. And this expression is initial value is 100, final value is 0. So 100 times e power minus t by tau 2. So if you want to combine and write the total Vc of t, then this is easy, right? This is just this expression is there for t greater than 0. So this is 100 times e power minus t by tau 2 u of t, and this expression is there for t less than 0, right? So 100 times 1 minus e power minus t by tau 1 u of minus t. So if you don't know, then u of t is this one, and this is u of minus t. This is time reversal, which will come in signals and systems. So u of minus t is 0 for t greater than 0 and 1 for t less than 0, and u of t is reverse. It is 1 for t greater than 0 and 0 for t less than 0. This is unit step function. So that is how you will write the expression of Vc of t. And similarly, you can write the current flowing through the capacitor. So Ic of t is simply dVc by dt. That you can directly write from this expression. You will directly get that. So actually there are two time dependent functions here. One is e power minus t by tau and one is u of t, and similarly here also. So if you want to differentiate this equation, then you will differentiate this one, keeping this as same, and then keep this same and differentiate this one. So yeah, if you don't know the differentiation of u of t, we can see that now. So it is simple. Let's say u of t, this is magnitude 1. So at t is equal to 0, it is going from 0 to 1, right? It means like within no time it is going from 0 to 1. So this is u of t. If you differentiate this one, then you will get something like, so this is constant which is 0, so if you differentiate that one you will get 0. So you will get 0, and here within no time, it means it is going from, if you want to write dy by dt here, then you will get 1 minus 0 by 0, which is infinite, I mean which is very high, which we can call as impulse. So at t is equal to 0 we have impulse function, and after that it is constant, so it is 1, so again it is 0. So this function we call it as impulse function, which is del of t. So du of t by dt is del of t, and du of minus t by dt is minus del of t. And if you take this expression, and if you differentiate this expression, then sorry, this should be c. So if you multiply with c, then you will get c times dv by dt. You will get that current. If you don't want anything here, so actually you will you keep this constant, and if you differentiate this one you will get del of t, right? Then again there is some property, if you multiply some del of t function with any some f of t, then you have to put t is equal to 0 in that expression, and that is all from signals and systems perspective. uh, if you don't want all this derivations here, you just have to write again the current. So this is all clumsy, right? So if you write the current expression in this circuit and in this circuit, then it is very simpler. You will get directly those two currents, and you can write the expression directly. So I think that is very easy compared to this approach. So we will write that one. So for this circuit, we will copy this one. Yeah. So for this circuit, I am saying the I of t, let's say it is I1 of t. So I1 of t is the final value. What is the final value? It is 0 plus initial value. Initial value is when it is short circuited. So when it is short circuited, it is 100 by 10 kilo, which is 10 milli. So final value plus initial value minus final value times e to the power minus t by tau 1 for t less than 0, which means 10 milli times e power minus t by tau 1. So if you draw the graphs, then you will have some idea on what is going exactly on the circuit rather than writing the equations. So let's say there is some, we have applied, we assume, right, we have applied that 100 volt at this point, right? So at the same point we are applying, and at this point it is 10 milliamps. So this is 10 milliamps, this is I of t, and when it doesn't know that there is some transient behavior is coming at t is equal to 0, right? So it is going to 0 amps final, and it will stay at that 0 amps, and the time constant here is tau 1, and it should be like this one. It is going from 0 to 10 milliamps, and it is coming back to 0 again, and here is happening, yeah, for t greater than 0. So I2 of t, I'm saying it as I2 of t. So what is the final value? Again it is 0, right? So for this one, final value is 0 because it is completely discharging, so there is no current flow further. And what is the initial value? Initial value is, if you uh, write at t is equal to 0 plus, then you will get this circuit. We will replace that capacitor with initial voltage, which is 100 volt, and there is some resistor, and yeah, this one. I think we derive anything here? This is R equivalent is 80 kilo ohm, that we got already. So this is 80 kilo ohm R equivalent, and this is 100 volt. So I of 0 is at t is equal to 0 plus, you can write 0 plus, or yeah, which is 100 volt by 80 kilo ohm. So I think it's 5 by 4 is 1.25 milliamps, yeah. So and this 1.25 milliamps is in this direction, but we are considering the current through the capacitor in this direction, which is IC of t, right? So this is IC1 of t, and this is IC2 of t. So if you take in the same direction, then minus 1.25 milliamps current is flowing in this direction, right? So at t is equal to 0, we have 0 amps, and then immediately it is going to 1.25 milliamps in opposite direction. So it is going to minus 1.25 milliamps, since it is capacitor, right? So it is allowing the sudden changes in the current, and finally it is going to 0, and this is tau 2, and this is 5 tau 2. So this is how the current waveform looks like. And if you write the expression, then you will get 10 milli e power minus t by tau 1 u of minus t plus correctly minus 1.25 milli times e power minus t by tau 2 u of t. Is this correct? Let's check once. So if you know this point, then it is, I don't think this expression is correct, so I will tell you why. So this we know, right? This is let's say I am right shifting this to here, this expression. So we will get is Vc1 100 times 1 minus e power minus t by tau 1. So 100 into 1 minus e power minus t by tau 1. Let's say I am left shifting to some very large time. I don't know this time. So this time is at what time we are applying the input voltage. If he has given, then it was very good, but yeah, let's take it as some t1. So if this time is t1, if we left shift this whole graph here, then it will become, so from 0 to it is going to minus t1. It means at t is equal to minus t1, if you substitute, then you have to get this value same as this value. You will get that when there is plus t1 by tau 1. This is left shift. It means you have to replace the time t with the time t plus this shifted value. So here we are shifting for t1, right? So here if you replace t with minus t1, then you will get here 0, which is same as that of if you write for when t is equal to 0. So these two are same. When you substitute, t is equal to minus t1. So this is the correct expression, I feel. So this is u of t, and similarly you have to write u of t plus t1. That is not the time reversal, that is the left shift. So here t plus t1 by tau 1 u of t plus t1, and I am calling this as minus t1 with respect to 0, and yeah, this is correct. And similarly here, so if you write that one here, if you right shift this one, you will get this expression, right, which is 10 milli e power minus t by tau 1 u of t. And if you left shift this one for time t is equal to t1, so which means this is minus t1 and this is 0, then we will replace here t with plus t1 by tau 1 u of t plus t1. So this is not correct. This is minus t plus t1 by tau 1 u of t1 plus t, and t1 is very high negative. Yeah, and this is the correct expression, I think. I'm sorry for that wrong expression here. This is more related to signals and systems, but I think you understand it. Final conclusion is, for right shift, replace t with t minus t1. For left shift of t1 units, here also of t1, then replace t with t plus t1. That is what we have done here. Yeah, this concept you understand, right? If you replace t here with minus t1, then you have to get this value same as that of this value. And suppose here at t2, and I don't know, then this will become minus t1 plus t2, right? So this is minus t1 plus t2. So in this expression, if you replace t with minus t1 plus t2, then you will get the same as the value at t2. You can cross check once. So I am replacing this t value with minus t1 plus t2. what you will get? 100 times 1 minus e power minus t2 minus t1. I am replacing this one plus t1 by tau 1 times of something something. So you are getting 100 times 1 minus e power minus t2 by t1, which is nothing but if you replace at this expression with t2, then you will get 100 times 1 minus e power minus t2 by t1, which is same as that of this one. So this is correct. So that is how the logic will work. So if you don't want to remember on everything, if you are confused, then you just remember this one. If you want to right shift, then replace t with the t minus t1, and for left shift you have to replace with the t plus t1. So I think we have gone more into signals and systems, and yeah, that is how the circuit will work. And the expression for this are some complex one, and I think it's done for today. And if you want to do some homework problems, and you can solve these two circuits, and this one and this one. Here I'm giving square input. This we can solve in next class. So I'm giving a square wave input, and the time period of that square wave is very much greater than RC. Much greater than means it is even higher than 5 times RC. It means uh, even the T by 2 also. It means we are waiting more time so that the circuit will reach to steady state, and then we are changing the voltage again here, and again we are waiting so that the circuit will reach to steady state, so that we can analyze easily. And this one you try to solve, and if you want you can also try what will happen if RC value is much greater than T. It means RC is higher, means it is taking more time to reach steady state. So if you want you can try this one also. And if you have any doubts, you can comment down. We'll try to solve. And if you like this video, you can share to your friends. Thank you.